Welcome back to our series of HRMAn tutorial videos. This time I'm going to show you how to use the second workflow that you can download from our homepage HRMAn.org, which can be used to train convolutional neural networks for use in HRMAn 2.0 to classify recruitment of proteins to pathogen vacuoles. Now this is an all-in-one workflow for which to run you basically just need images of infected host cells stained for the protein of interest for which you want to train the model, and you will also need a good computer with a GPU that is able to run GPU accelerated calculations for training of the neural networks. Best to have a GPU with as much VRAM as possible. I'm using a NVIDIA GTX 1070 with 8 GB of VRAM, could be better though. Now for the images that we're going to use today, I have images from two wells of a multi-well plate, well B7 and well B9, overall 80 fields of view for each well, so 160 in total, to have enough cropped pathogen vacuoles for training of a good model. And the way the images look like, you can see here in this preview, we've stained the cells for the nuclei, then we have the fluorescent Toxoplasma gondii, and then the host cells stained for ubiquitin. Now to run this workflow, you can just download it from the homepage and load it into your NIME that's been configured for use of HRMAn 2.0. And then it looks very similar to the main workflow. It also has steps that can be run one after the other, or should be run one after the other. And we're just going to start doing that now. So one limitation is that the models that we're training are only for a single stain. So we can only load images that have 3 channels, always the nuclei, the pathogen, and then the recruitment stain. First step is to point the pipeline to the folder that contains the images, which in this case is on my desktop, so you can just use this browse button and then navigate to this folder images and open and click OK. And once this has been loaded, you can execute this node by either using this little button up here or right-clicking on it and selecting execute. When it has finished, we'll start with actual loading of the data and the pre-processing, followed by the segmentation. So this part works exactly as in the main pipeline HRMAn 2.0. So we select here, right-click, and then choose execute. Now it's going to need a bit of information, just like HRMAn 2.0. So these images were imaged with a magnification of 63x. We have a pixel size of 0.2 micrometers per pixel. We have infected the cells with toxoplasma. That's all correct. Then we need to assign the 3 channels. So the order was channel 1 nuclei, channel 2 pathogen, channel 3 cells. That's okay. Correct. We have only imaged a single Z-plane. And we want to do the classic segmentation for the nuclei and also for the cells. The images, as I showed in the beginning, come from 96 well plates, and they were in well B7 and well B9. They have both been infected, yes. This is correct. And now HRMAn's going to go to work. Now that the first part is finished, we can move on to the next step and select this image viewer here and execute it. And we can then make sure that all the images have been loaded correctly into the program and assigned to the right channel, which is the pathogen, the nuclei, and the stained cells. And this is looking good. Scrolling through all the images. Perfect. So we can then start the segmentation, and we're going to begin with the nuclei. Selecting this node, again right-clicking and executing, and we'll wait until it's finished. Now that it's finished, again we'll make sure that the segmentation is good, and you can do this by just right-clicking on it and opening the view, and you can then click into the images and compare the outline with the actual image, and you can also change the transparency of these outlines here, or change their color to visualize it better. And we can see it's done a pretty good job here detecting all the nuclei of these cells. We'll then continue the same thing again for the pathogens. Select the node and execute it and wait until it's done. Okay, now that this has finished, we'll take a look at the segmentation of the pathogens. Again, open the view and click into it, and we can see it's done reasonably well detecting all these pathogens on our images. Now, the last thing for the segmentation, we need to repeat this for the cells. So again, execute the next and wait until it's finished. And now that it's finished, again, inspect the segmentation by opening the view. And you can't see any cells here, but we can see the cells here. And it's done rather well detecting all these cells. One thing to note here is that cells that are touching the border of the image are not removed. Since we're not counting the pathogens, it doesn't matter if they're incompletely captured. We're mostly just interested in capturing as many of these recruited vacuoles here as possible. Now that all the segmentation has been done, we can go to the next step and execute this node, which will finish up the segmentation and then prepare all the images for annotation. And once this is completed, a little annotation window will open and you'll see what that looks like in just a second. Okay, as you can see now, when this part of the analysis is running, at some point these windows will open, which can then allow you to annotate your images. What you see, overall 1013 vacuoles have been detected from our 160 original input images. And the program shows you the crop of the image with the pathogen and the stain, and the context ROI highlighted here in yellow. And you can then just simply use these buttons down here to annotate all of these images, which I will now start doing, and I'm probably going to speed up this part of the video because it's a rather tedious process, but has to be done before training the neural networks. So now you can see we're nearly done here. I've arrived at the last image, and if you've watched closely, you could see I also had a few images in there that I mixed in on purpose that I knew would create artifacts. So this class is also represented. Now once I click here on the last image, it's just going to randomly pick a few more to assess how good my annotation is. So I'm just going to go through these real quick. And now that I've gone through the randomly picked ones again, apparently my quality or consistency of annotation is just 93% today, meaning that probably 2 of the images I have just like annotated in a different way. However, for now this is okay. Ideally you want this to be as consistent as possible. So if you keep practicing, you will get better and your annotations will become more consistent. I'm going to confirm this by clicking OK. And it's then going to write all of these results to a result table. So you have the parameters here, the size of your images and your pixel size, and your assay layout. So here it's just well B7 and well B9 from which our input images originated, and then all of our annotations. So you see each cropped vacuole image has gotten its unique identifier, and it's written down the status here. 0 for no recruitment, a 1 for recruitment, and if we go further down towards the end, you'll see some 2s here which mark artifacts. Now, the next step is sort of a breakpoint, so I'll just click here and save the files, and it tells me that overall I have annotated 1013 pathogen vacuoles, of which 554 were recruited, 306 were non-recruited, 316 were recruitment, and 143 were artifacts. Now that one class contains fewer than 200 images, the program encourages me to considering annotating more images, since you want to have a decently sized dataset for training of the neural network. Now, where are all these files located? They are in your input folder that originally had the images. Your original images have been written into an archive folder for long-term storage. You will find the Excel table that had opened previously here that holds all the annotations. And you will find a folder with the cropped vacuoles. And one folder has the cropped cells with the regions of interest for context highlighted. One folder has the PNGs of the cropped vacuoles. And one folder has the actual normalized images of all the cropped vacuoles. And you can see they all have this unique identifier with which you can link them to the annotation. And these ones are then actually used for training of the neural network. Now there's another file here, which is called datatable.table. That's the KNIME internal data file. And you can, for instance, if you decided you want to abort the analysis here and don't continue with the training, you could run through this whole process a couple of times. And then you can use these table readers here to read in your files, to optionally add more data sets. And then connect these connections here and the concatenation node to the next step of the analysis. However, even though one of my classes now is a bit underrepresented, I'm still going to continue the analysis for the purpose of this demonstration. And the next step is the data partitioning, which partitions your training data, and 90% for training and keeps 10% aside for validation, and it also augments the images by turning and flipping them around, so that we'll get a decently sized set for training. I'm going to execute this and I'll be back once this has finished. Okay, so now the partitioning and augmentation has finished, and from this step a couple of things are passed on to the Keras network learner. This is the node that actually now trains the neural network. The first thing that is passed on via this red connector here is the empty or untrained neural network model that has been initialized with random weights and biases. The second thing that's passed on is our training data set, which now has 128,250 images. And the last thing is our validation data set, which just has 671 images. And the way these tables look like, you have the input image, and then you have your classes with the respective probability. So here we have an unrecruited vacuole, this would be an artifact, and here you would see a recruited vacuole. And these images have also been randomly shuffled, so that in each batch that's going to be used for training, there will be a representation of each class. Before we run this network learner, one word of warning: I wouldn't try to run it without GPU acceleration, because even with GPU acceleration, this can take several hours up to several days. And before we run it, we're going to configure, make sure that all the configuration is right. It has been pre-configured, but it's always good to double check. And to do that, you can just double click on it, and then this menu opens. We're going to make sure that our input data is selected as the image, and from image auto mapping as the conversion method. Target data is our 3 classes and the probabilities for them, and the conversion is from number. And as the loss function for the training and evaluation, we're going to use the categorical cross entropy, since it's more than 2 classes. Then in the options, this has been pre-configured to work with my particular GPU. We're using the TensorFlow backend. This you shouldn't change. We're going to train, in this case, for 120 epochs, even though you can terminate the learning early. And we're going to use a batch size of 96 images per mini batch. If you have a more powerful GPU, you can increase this. If it should fail allocating enough video memory, you should reduce this. And we're going to leave this box ticked, which means that it's going to reshuffle the training data before each epoch. The optimizer, we're just going to select Adam with a learning rate of 0.0001, and the other parameters we're not going to touch. In the advanced options, you can select to terminate the learning early upon no loss or upon training stagnation. I'm going to use to reduce the learning rate should the training arrive on a plateau and not progress further. And these are the settings for this. So the factor by which you drop your learning rate, the patience, and the cooldown, and the minimum learning rate. So we're all happy with this, so we can close this menu by clicking OK, and then we can right click on here and execute. And this is now going to start training of the neural network. And you can follow the training, so if you right click on here while it's executing, you can right click on it and choose the view learning monitor, which at the moment has nothing to display, but as soon as the training starts, we can follow the progress here, which should be in just a minute. Okay, so now the training is running, and in this learning monitor you can follow the training live as it progresses. You can see a few things. You can look at the current accuracy. In this case it's the training data, because we haven't arrived at the end of an epoch where it uses the validation data, but you can see the current accuracy here. You can see the progress down here. You can also use smoothing of this curve. We can also, instead of looking at the accuracy, we can look at the current loss, and we can also look at the log output. One thing that I can recommend is that while this is running, to monitor your GPU usage with something, for instance, like GPU Z. Where we can see the current clock speeds of the GPU, the memory usage, as well as the temperature. And we can just, since this can run rather long, can make sure that the GPU is not suffering too much by, for instance, adjusting the fan speeds if we should see that it gets too hot. And I'm now going to speed this up a lot, and we can follow the training of this model for a while. So now that you've seen how it looks like when this model trains, so you can see even though we're still early in the learning, the accuracy is increasing. So we're starting at something like 35%, which is with 3 classes just a random guess, and are rather quickly increasing. At the same time, our loss is quickly decreasing, and meaning that the model is converging. I'm going to stop the training here now because for the purpose of this tutorial, it's enough. Obviously, we're not getting good results for our validation data set yet. But since we're anyways not going to use this model in future, it's good enough to illustrate this. So if you want to terminate the learning, you can just click here on stop learning. And it's then going to stop this execution. We can close this, and now you just need to wait until this traffic light underneath here jumps on green. One warning, don't use the cancel execution, because that actually cancels the execution and doesn't stop it, which means you will lose the model. Now that it's green, we have a trained model, and we can continue with this next node, which is going to evaluate the model. So it's going to take our validation data set and run the newly trained model for the prediction, and is then going to also save the model and calculate some accuracy statistics, which we can then inspect in just a minute. Okay, so this has finished. So first we can execute this node, and at the same time also already execute the next one. We can have a look here at the accuracy statistics if we go to this interactive view JavaScript table view, which will open a new window. And we can then see here our true positives, false positives, and so on, recall, precision, and in the last table also the accuracy. So the model that we've trained only achieves 84% accuracy, which obviously if you would train it longer and with more input images and more examples for each class, would help to generalize the model and make it perform much better with accuracies up to or even above 95%. Now also the other one with the heat map and the confusion matrix has finished, so we can take a look at this as well. And you can see here, so the classifications definitely work well. So we have the more green, the more close to 100% of all predictions, and you can see across it looks good. Where it seems to struggle at the moment is to distinguish between unrecruited and recruited vacuoles, since there are a couple of probably about like 20-25% misclassifications in this class, whereas it's already really good in singling out the artifacts, and this would then probably be, with longer training, this issue would be resolved, or more input images. Now that everything is finished, you can go back to your input folder, and you will then see this file here with the trained model and the appended accuracy, and this can then be used in HRMAn 2.0 to perform recruitment classifications. And with this, I'd like to thank you and wish you good luck in training your own models and using them within HRMAn.